Hi, George Romanic here. In today's video we are going to continue our investigation of finding a probability of air atoms escaping gravitational pull of our planet. In my previous video we calculated the escape velocity, which is the velocity that any object needs to have to escape gravitational pull of Earth, and you will remember that velocity was 11.2 kilometers per second. But now we are not interested in any object, perhaps this hammer, but we are interested in air atoms escaping gravitational pull of our beautiful planet. And these air atoms have distribution of speeds, and that distribution is the powerful Maxwell-Boltzmann distribution. So we will combine that distribution from kinetic theory of gases with the concept of escape velocity from the law of gravity to find the probability of air atoms escaping gravitational pull of our planet. Then, if you wish, on your own you can apply the same equations to investigate the probability of an atom escaping gravitational pull of the Moon or Mars or some other planet. And you will get great insight into composition of atmospheres of different celestial objects. I have to warn you, today's video is advanced video. Integrals that we will encounter are nasty. They are nasty to the point that some of the integrals cannot be solved analytically. So we will have to introduce error function, complementary error function, all this beautiful complicated mathematics that will give us result that is breathtaking. Think about it, we will get result that will tell us what is the probability of an air atom escaping gravitational pull of our planet. You can get such a beautiful result only through the powerful tools of sciences, and particularly atmospheric sciences and physics. Before we start, I would like to ask you to share this video with several enemies and perhaps even friends and family. Now let's start solving this problem. In the previous video, we saw that escape velocity for planet Earth is 11.2 kilometers per second. Now we want to combine this with Maxwell-Boltzmann distribution of velocities to find probability of atoms escaping Earth's planet. Well, you will kindly remember that Maxwell-Boltzmann distribution looked like this. So if here we have velocity v, and here is f of v, which is probability density function for velocity, then for a given temperature, the distribution might look like this. So it is skewed to the right, and there is this peak, which is the most probable speed or mode speed, Vmp. And I have entire video that specifies how to find Vmp. However, in this video, we are not interested in this speed. We want to attach our problem to this escape velocity Ve. So let's say this Ve is somewhere here. This is escape velocity, 11.2 kilometers per second. And we want to find probability of an atom having velocity V larger or equal than this escape velocity Ve. That is the question mark for this video. If you look into this probability density function, you will see that we are interested in solving integral between Ve and infinity for this probability density function, namely finding the area under this curve from Ve to infinity. So let us do that. If we continue this expression, what I just said is that we need to find integral between Ve and positive infinity of this probability density function f of v dv. We know from my previous videos the form of Maxwell-Boltzmann distribution, namely that would be square root of m divided by 2 pi kt everything to power 3 times 4 pi v squared e to negative m v squared over 2 kt and then dv, where m is mass of an atom, k is Boltzmann constant, T is absolute temperature in Kelvin, and everything else is defined, and of course integral goes between VE and infinity. We can make this integral look nicer because this is constant, 4 pi is constant, so I can write 4 pi and then square root of m divided by 2 pi kt to power 3 integral between VE and infinity v squared e to negative mv squared over 2 kt dv. Now this integral we will start solving it by introducing substitution. And substitution is that mv squared divided by 2 kt is some new variable. But for shortness I will first introduce a constant c, new constant, that is equal m divided by 2 kt. So just not to drag m2 kt everywhere, I introduce this constant c. But new variable, more importantly, let's call it x squared, will be defined as this c times v squared. And I hope that you can see from here right away, if I take square root of this expression, that x will be square root of c times v. Now from here, notice that if I differentiate this, I will get that 2x dx is equal 2cv dv. 2 and 2 will cancel. And from here I get that v dv is equal x dx divided by c. But x I can substitute here to be square root of cv, so I get that right hand side here is square root of c times v times dx divided by c. And now notice that v and v cancels, and at the end I get that dv is equal dx divided by square root of c. Now with this substitution and this change of differential variable, I can go back to my integral and write that p is equal, let me first write like this, 4 pi, I will copy this part, square root m divided by 2 pi kt to power 3 integral. What would be new limits? Well, when v is equal ve, x will be square root of c ve. And when when v is infinity, then x will again be infinity. So these are my new limits. Now v squared, that will be, as you can see from here, x squared divided by c, and then I have e to negative, this whole thing is just x squared, and dv, well, dv is dx divided by square root of c. Now you can see that this constant c also appears under this square root. So here, let's manipulate this square root to get nicer expression. You can see that this term over here is 4 pi, and then this square root I can write as c over pi, everything to power 3. And then I can divide by, as you can see, this c, and this square root of c, that would be c to power 3 over 2. Now this is further equal 4 pi c to 3 over 2 divided by pi to power 3 over 2 c 3 over 2. And notice how c 3 over to power 3 over 2 and c to power 3 over 2 cancels. And here I get that this is simply equal 4 divided by square root of pi. Now with this nice mathematical simplification, I go back to my integral p and I write that this is 4 divided by square root of pi integral square root of c ve to infinity x squared e to negative x squared dx. And this is now new integral that we need to solve. To solve this integral, I will rewrite it in the following way. I will say this is 4 divided by square root of pi. And then I rewrite this as following. Integral between 0, not this limit, but 0 to infinity of x squared e to negative x squared dx minus integral between 0 to this limit now, square root of c ve x squared e to negative x squared dx. What is this sorcery, you might say? Well, this is very actually simple. Let's say here is 0 and my axis x-axis is going like this all the way to infinity. So let's say infinity is somewhere here, just for good measure. Somewhere here is square root of c times ve. You see, integral between square root of c ve to infinity represents this part on my axis, let's say. But I can write that clearly as 0 to infinity, which would be this, minus this segment over here. And that's exactly what I wrote here. So 0 to infinity, minus 0 to square root of cve, minus 0 to square root of c times ve. At the end of the day, I get this, which is exactly this integral. But I'm rewriting this because this is enabling me to solve independently these two integrals in a way I would not be able to solve this integral with these particular limits. Namely, I will call this integral from now on I1, integral I1, and this integral I will call integral I2. So integral I1 is equal integral between 0 and infinity x squared e to negative x squared dx. Before we start solving this integral, you will kindly remember that this integral looks somewhat similar to Gaussian integral. And let's write here, you know I have entire video on Gaussian integral, that Gaussian integral is very particular integral with the limits between negative infinity and positive infinity, e to negative x squared dx. And this integral has analytic solution, closed form solution, and that is square root of pi. And I have video where I solve this integral to demonstrate this. So you see this integral over here has some features of this integral. It has e to negative x squared, but also has this term over here, and the limits are not the same. But we will use this later in the solution of this integral, as you will see in a few minutes. This integral can be solved using integration by parts. You will remember another note that integration by parts says if you have integral f dg, then this integral is equal fg minus integral g df. Let x, not x squared, by x be my f. From here, we see that dx is df. And let dg consequently be x e to negative x squared dx. Then from here, g is equal integral x e to negative x squared dx. Now you're saying this is getting more and more complicated. How do I solve this integral? It is getting more and more complicated, but that's how the universe works. To solve this integral over here, we introduce a substitution. And substitution is that this negative x squared will be some new variable t. So it means that negative 2x dx is equal dt. Or x dx is equal negative dt over 2. Now with this substitution, I go back to my integral g, and notice that g will be equal negative 1 over 2, because that's x dx is dt over 2. So integral e to t dt. And finally, you can see this is table integral that is equal negative 1 over 2 e t. But t is negative x squared, so this becomes equal negative 1 over 2 e to negative x squared. Now let me go to the next page. So now with solution of this integral g, I can go back to my integral I1, and I can write that the integral I1 is equal f times g, but f was x, and g, I just showed you, is negative 1 over 2 e to negative x squared in the limits between 0 and infinity minus integral between 0 and infinity, and then kindly remember we have g df, and g is this and df is dx. So we have negative 1 over 2 e to negative x squared times dx. Or I can write this to be equal the following. So you see here we have infinity, so I have to take negative 1 over 2, and then I have to take limit when x tends to infinity of x, that's this, divided by e to x squared. Not negative. It was negative here, but when I bring it down, it's just x squared. And then minus, bottom limit is 0. Well, this is just 0. And we have then minus and minus, that will give me plus, integral between 0 and infinity. This 1 over 2 can come in front of the integral, and I will have e to negative x squared dx. Now we have to solve this limit. Notice that limit when x tends to infinity of x divided by e to x squared, when x tends to infinity, this is infinity and this is also infinity. So this is infinity by infinity. Whenever you see this, your eyes are glowing, because you have to use the great and powerful L'Hopital's rule, which says that this limit is equal to the limit when x tends to infinity. Take derivative of numerator, that's 1. Take derivative of denominator, that's 2x e to x squared. And now evaluate this limit, And if you do it, you will see that this is still tending to infinity. This is 1. So you get 1 over infinity, and that is clearly 0. So this limit is also 0. So we get here 0 minus 0, that's 0. Well, that further means that my integral I1 is equal 0 minus 0 is 0. So I get 1 over 2 integral 0 to infinity e to negative x squared dx. But now we go to my note on the previous page, because my note says that integral between negative infinity and positive infinity e to negative x squared dx is square root of pi. And notice that here we have the same integral, but the limit is between 0 and infinity, so this integral has to be half of this integral. Which means the solution is 1 over 2, this constant, square root of pi, that's Gaussian integral, but this is half of it. Which means my integral I1 is really square root of pi divided by 4. Okay, so going back to this expression over here, notice that we solved integral I1. So I will go back to my integral P and write that P is equal 4 over square root of pi, that was constant, that was multiplying integral I1, which is square root of pi divided by 4, minus this integral I2. And that would be integral between 0 and the square root of c times escape velocity, x squared e to negative x squared dx. And notice that this is equal, well, these two will cancel, so I will get 1 minus, if I multiply this factor with this integral, I will get 4 over square root of pi integral between 0 and the square root of c ve times x squared e to negative x squared dx. Now this integral over here, which I called integral I2 on the previous page, cannot be solved analytically. We cannot do it analytically. But we can massage it a little bit to get to expression where we can identify it with the so-called error function. And I have video on error function. This relaxing massage of integral I2 is the following. I will rewrite this expression as following. This integral p will be 1 minus. Now, instead of 4 over square root of pi, I will write 2 over square root of pi, okay? Integral between 0 to square root of c ve. Instead of x squared, I will write x. And then I will have e to negative x squared. And now I have to add 2 to get 4. And I have to add x to get x squared dx. Okay? I just rewrote this expression. Now, let's do another note over here. If I take derivative d of this expression, negative e to negative x squared, then derivative of this will be, of course, negative 2x e to negative x squared, but this negative that comes down will cancel with this one, so I will get plus 2x e to negative x squared. But now you will kindly notice that we have this 2x e to negative x squared in our integral over here. So I can write that p is equal 1 minus 2 square root of pi integral between 0 square root of c VE, and I will write x, and then this over here is d of negative e to negative x squared. And now this integral I can start solving by using integration by parts. So I will say that x is equal some function f. So we see that therefore dx is df. And I will say that this crazy expression d of negative e negative x squared is my dg. Well, from here it follows that g is simply equal negative e to negative x squared. So my integral p therefore becomes 1 minus 2 over square root of pi, and then I will have f times g. Well, f is x times g, well, that's minus e to negative x squared, and that needs to be evaluated between 0 and the square root of c VE, minus integral between 0 and square root of c VE, g df, but g is negative e to negative x squared, df is dx. Now this is further equal to 1 minus 2 over square root of pi. So I will have negative square root of c VE e to negative c VE squared, and then when limit is 0, well, this becomes 0, so it will be minus, and this minus give me plus 0, and then we have further plus, because this minus and this minus will give me plus, integral between 0 and square root of c VE e to negative x squared dx. Or I can write that integral p is equal, this minus and this minus will give me plus, so 1 plus 2 times square root c over pi, when I combine these, times VE times e to negative c VE squared, minus, when I multiply here, is 2 over square root of pi, integral between 0 and square root c VE e to negative x squared dx. And you will kindly remember from my video on error function that this over here is the exact form of the error function. In other words, you will remember that error function of, let's say, some variable y, okay, is equal to divided by square root of pi integral between 0 and y e to negative t squared dt, where t is of course some dummy variable. And you can see this is exactly that expression, which means I can write that my probability integral p is equal 1 plus 2 times square root c over pi VE e to negative c VE squared minus error function of square root of c VE. But we can simplify this even more, because there is the so-called complementary error function defined as ARFC, complementary error function of some variable y, which is equal 1 minus error function of this variable y. So you can see, if we would rewrite it, in terms of the integral, we would get that this is 2 over square root of pi integral between y and infinity e to negative t squared dt. Let me try to maybe explain a complementary error function even better. If here you have a variable, let's say u, so let us say this variable u, it has to be Gaussian variable, so it's normally distributed around this origin. Maybe my figure is not the best, but you get the point. This should be normal distribution. Then error function is taking integral, as you can see, between 0 and some y. So here is 0, and let's say here is my variable y. So this integral over here would be ERF, error function. And this integral, I told you in separate video, cannot be solved analytically when this curve is Gaussian curve. So you can clearly see that the complementary error function would simply be not this, but rather this over here. That would be ERFC, complementary error function in this case. Of course, this works because if here is y, here is negative y, here is positive infinity, here is negative infinity. This entire integral from negative infinity to positive infinity is, as I said, Gaussian integral, which does have analytic solution, but the integral only has this solution when the limits are between negative infinity and positive infinity. When the limits are something else, then we have to introduce this error function, and now you understand how error function is related to Gaussian integral and how in turn it is related to the complementary error function. Now let us go to the next page. So going back to my integral p, I can write that this is equal complementary error function of square root of c times ve plus 2 times square root of c divided by pi and times ve times e to negative c ve squared. And you will now remember that at the very beginning of this video we define c to be m divided by 2kt. So when I substitute that over here, I will finally get that this probability integral p is equal error function complementary of square root m divided by 2kt times ve plus 2 square root of m divided by 2 pi k t times ve times e to negative mve squared divided by 2kt. And after a long 40 minutes or so, we get our solution. If we plug in numbers over here, and I did it for hydrogen, for helium, for hydrogen in molecular form, and I also did it for oxygen, just for good measure. Because you will see that these probabilities depend on masses. The heavier the atom, the smaller probability of escape from Earth's gravitational field. And here is something to convince you. Let us first look graph on the left. X-axis is temperature in degrees Celsius. Y-axis is probability of escape calculated using this expression over here. And you will see that I did it for hydrogen and hydrogen in molecular form. You will see that probability is really not negligible for hydrogen atoms at high temperatures that we often see in thermosphere in the atmosphere. For helium, you can also see that the probability is not negligible. Keep in mind that the scale of y-axis is not the same here. But really for oxygen atom, probability is effectively zero. So oxygen atoms are too heavy to escape Earth's gravitational field. This, in part, explains why our atmosphere doesn't have that much helium and doesn't have that much hydrogen as well. Now, hydrogen is also a quite reactive element, so it reacts chemically with other elements in the atmosphere, but helium is quite inert, but it slowly escapes our atmosphere. So residence time of helium in our atmosphere is about 1 million years. And 1 million years, believe it or not, is not that long period for our planet that is approximately 4.5 billion years old. If you want to know more about this theory and probability of escape of atoms from our atmosphere, you can read paper of Kokartes from 1973, and it's a beautiful study where he developed much more comprehensive theory than what I did in this YouTube video, but nevertheless, the basic idea is the same. We have to use some underlying distribution of speeds. Our underlying distribution is great and powerful Maxwell-Boltzmann distribution. Just to connect, what are these different temperatures in respect to our distribution? So if this is temperature T1, some temperature T2 that is larger than T1 would have distribution that perhaps looks like this. Okay, so the peak is shifted to the right, it lowers, but the probability of finding atoms of higher speeds increases, and of course I discussed this in great details in my video on Maxwell-Boltzmann distribution. I assume you know Maxwell-Boltzmann distribution if you are watching this video. If not, I do have video on that. So you can see that probability depends on temperature because temperature dictates probability of finding atoms with different speeds. This theory also tells you why Moon effectively doesn't have atmosphere. Because the Moon has very low escape velocity, not like Earth, 11.2. I don't know what is escape velocity for the Moon. You can check online and let me know in the comment section below. But velocity is much smaller, and therefore probabilities of atoms escaping Moon's atmosphere are much higher. These probabilities are much higher. The same is, let's say, for Pluto, which is planetoid. The same is for any lighter planet than our beautiful planet Earth. Beautiful mathematics, beautiful derivation, and even more beautiful result. I hope some of you will use these equations to calculate probability of atoms escaping gravitational pull of different celestial objects. If you do that, please let me know in the comment section below, for example, what is the probability of a helium atom escaping gravitational pull of the Moon, or a hydrogen atom escaping gravitational pull of Mars. Until next video, goodbye.